thanking Tapas Shauli for the organizers of this conference and all of you for coming. And it's good to see everybody again. Many of you were concerned about my well-being, and I just want to tell you that I'm good for another 50 years. Okay? All right. So this is about transcendental sums related to zeros and the Zeta function. And it is joint work with Shauli and Purusottam Rath. And so the interesting thing is this work is at least 4 years old, and we finally completed it and recently to a journal. The motivation for our research emanates from an amazing criterion for the Riemann hypothesis called the Lie criterion. So I want to explain that. So let's recall that the Riemann Zeta function defined by this Dirichlet series in the region real part s bigger than 1. And in 1859, Riemann, we can apply he also showed a functional equation namely pi to the minus s over 2 gamma s over 2 zeta of s equals pi to the minus 1 minus s over 2 gamma of 1 minus s over 2 S. So the functional equation gives us a line of symmetry, the line of symmetry being real part S equals 1/2 is the line of symmetry. And so there's the famous Riemann hypothesis that he formulated. That all the zeros of all the non-trivial zeros of the zeta function, all the zeros of zeta of x in the region 0 less than real part s less than or equal to 1 are on the line So this is the famous Riemann hypothesis. As of today, it's still open. And much research has been done on the Riemann hypothesis. For example, Murty showed that infinitely many zeros firstly are on the line real s equal to 1/2. And then Selberg showed that there was a positive density of zeros on the line 1/2. Montgomery, Levinson, and Conway showed that there were that more than at least a third of the zeros are on the line. So a lot of progress has been made on this. We're still seem to be very far away from the Riemann hypothesis. In 19 let's see, 19 1997, Jianjin Li there are a lot of Lees, I thought first name down. Jianjin Li gave a for the Riemann hypothesis. And look at numbers, lambda n, sequence of numbers, where you sum over the non-trivial zeros. Look at 1 minus 1 over rho to the power n. So these are the zeros of the zeta function, and they lie in the region between real part 0 and 1. You look at these numbers, and Lee showed that the Riemann hypothesis is equivalent to lambda n's being non-negative for all n's. Beautiful criterion, very elegant, symmetric, and intriguing. And we haven't been able to show this yet, of course, as you know. And so the question arises: so what does all this mean? And can we say anything about it? And many people have started to look at these sums. So here, as you can see, it's some sort of polynomial or rational function. So this is some sort of rational function. In rho. If you take the common denominator, basically what I'm saying here is that this is equal to rho to the n minus, taking it, you take basically 1 minus rho minus 1 to the power n over rho to the n, so that's basically rho to the n, rho to the n minus rho minus 1 to the n. So you have a function here, which is, this function looks like this, and you're trying to show that these sums are all non-negative. So it suggests, as is often the practice in mathematics, sometimes trying to understand some sequence of numbers, this motivates the study of more general sums, study of more general sums like summation A of rho over B of rho, where A of x and B of x are polynomials. And in this case, they're polynomials with integer coefficients. So we may want to look at maybe polynomials with algebraic coefficients.
One small question. These zeros are countably many.
Yeah.
These zeros, which lie, whose real parts lie between the strip 0 less than equal to real part of rho less than equal to 1.
Yeah.
They must be countably many, maybe.
They're countable, yes.
Okay.
Yeah.
If they were uncountable, maybe they will have a limit.
No complex analytic function can have uncountable zeros.
Otherwise, yes.
One typo is maybe that one mod lambda is that rho is complex.
Mm-hmm.
One mod maybe.
What?
No mod. Okay.
Where
conjecture is no mod. No, lambda is greater than equal to 0.
Yeah. No mod. Lambda, and those are all real numbers. That can be shown by the functional equation.
Oh, that follows.
Those are all real numbers. So it follows from the functional equation that this is a real number. Therefore, it's just have to show that they're not negative. So this particular criterion of Lee motivates the study of sums of this nature, And we generalize this study to perhaps look at more general sums like this with some variable x. Don't confuse that x with this particular. So we look at this function. So we may consider this function of x given polynomials a of x and b of x. We consider this particular expression, and we want to investigate what one can say about the zeros of the nature of these numbers. So we may want to investigate what is the nature of this function. What's the nature of this function? What are the values it takes, and so on and so forth. So this is basically general philosophy, just general motivation for looking at this question. Let me update you on the tantalizing progress that has been made in the study of Lie criterion. So these sums, lambda n, coming back to the lambda n, we can simplify them a little bit. So the lambda n's can be simplified in a variety of ways. They can be simplified through the study of the Stelz's constant. So let me explain to you the Stelz's constant. So if you look at the Laurent expansion of the Riemann zeta function, the Laurent expansion of the Riemann zeta function about s equals 1. Most of you know that it starts out with 1 over s minus 1 plus Euler's constant. And then you have these other n going from 1 to infinity, minus 1 to the n, gamma n, over n factorial, s minus 1 to the power n. So the higher constants are called the Stelz's constants. And these numbers will appear in the study of the lambda n's. And just to give you an idea of what's involved, let me point out that if I look at the logarithmic derivative of the Riemann zeta function, which appears, of course, in the study of the distribution of prime numbers, this begins as 1 over s minus 1, and it's a small exercise to study these constants and relate them to the gamma n's. So let's call these etas of n's, s minus 1 to the power n. And you can relate these constants in the following way, the recursion formulas. So let's see, eta 0 is minus gamma 0, which is gamma. So this is gamma 0. Eta 1 equals minus gamma 1 plus 1 half gamma 0 squared. Eta, etc., etc. So you can see that the eta sub n's are related to the gamma sub n, the Stelz's constant. And here's an interesting, curious exercise, which I leave you to do. Curious exercise. The Riemann hypothesis is equivalent to the assertion sum over these non-trivial zeros and take 1 over mod rho squared, this turns out to be equal to 2 plus Euler's constant minus log 4 pi. So you may want to amuse yourself by trying to prove that, not during my talk, but afterwards. This curiosity actually motivated Shaoli and Purusottam and myself to study the nature of numbers that seem to arise. I mean, what kind of numbers are, we certainly expect gamma to be transcendental, log 4 pi to be transcendental. Maybe these are all transcendental numbers. And it's just an interesting question from that perspective. What kind of numbers come up as special values of this function f of x? And that's the motivating theme for our research. The general formula then, now that I have defined to you these delta constants and these other constant eta sub n's, let me point out that lambda n, so this curious exercise number 1, but this is just this is not a curious exercise, it's a routine exercise number 2, which tells you that lambda n can be written in terms of the eta j's, minus summation j going from 1 to n choose j, eta j, plus 1 minus log 4 pi plus gamma 0. When I write gamma, I just mean gamma 0, n over 2, minus summation j going from 2 to n, minus 1 to the power j minus 1, j, 1 minus 2 to the minus j, zeta j. So here's a really very neat and beautiful formula. So the eta sub n can be written down in terms of the Selberg constant and these numbers, and then special values of the Riemann Zeta function. So the Riemann hypothesis is actually equivalent to the positivity of these Laurent coefficients somehow mingled in this way. And so it is possible to decompose this particular quantity into various parts and convince ourselves that probably the Riemann hypothesis is true. Because we expect these numbers to be, certain numbers to be very, very big. So it is possible to show that lambda n, so one can, so curious exercise 2, number 3, you would then show that lambda n equals 1 minus n over 2 gamma plus log 4 pi plus S1 of n plus S2 of n. And S1 of n is equal to summation j going from 2 to n choose j, minus 1 to the power j, 1 minus 1 over 2 to the j, zeta j, and S2 of n is equal to j going from 1 to n choose j, eta sub j minus 1. And Coffee showed that
minus sign is 2.
So
Minus sign.
Pardon me?
There is a sign.
Where?
For S2. S2n. Minus sign.
No.
If you compare here.
Oh, there's this here. I got, yeah, you're right. Maybe there is a minus sign. Okay, let's put it in. Yeah, maybe there's a minus sign here. So in that thing, let's put a minus sign. All right. So Coffee showed that S1 of n equals That's the Riemann. 1/2 n log n plus gamma plus 1 minus 1. 1/2 n log n plus gamma minus 1 plus 1. Sorry, there's some typos here. 1 log n plus gamma minus 1 plus 1. Now this is so you have, the fact is that this lambda n can be decomposed into these 4 parts. And we see that S1 of n is growing like n log n. So supposing we could manage to show that lambda n's are non-negative for n sufficiently large, that would be practically equivalent to the Riemann hypothesis. So S1 of n is already quite big as n log n. And because n log n is larger than this quantity, so these two things are sufficiently positive, so the cancellation is okay. And so the whole activity with respect to the Riemann hypothesis then is centered on the study of the Skelcher's constants. Right? So therefore, that is the focus of attention. So the non-negativity of the lambda n's is then reduced to the study, the detailed study of these Skelcher's constants. I think this is very fascinating. And I believe this probably attracted the attention of Bomburi and Logarithmic, so who in the year, when did they show that? Bomburi and Logarithmic in 1999 showed that we can reduce the, we can weaken the condition. You don't have to show non-negativity of the lambda n's as long as you can show the much weaker thing. The Riemann hypothesis is equivalent to the condition that for any epsilon positive, there exists some constant positive such that the lambda n's are bigger than minus c of epsilon e to the epsilon n. In other words, we don't care if the lambda n's are negative as long as they have sub-exponential growth. That's a big reduction in the thing. So it's possible. It's interesting that how things refine themselves. So all of this is very promising for anyone who's trying to pursue or understand the Riemann hypothesis. So I hope I have sufficiently motivated your interest in convincing you that probably sums related to the zeros of the zeta function of this form are interesting. And perhaps while we're at it, we can study functions with some argument, because these kind of sums look like they are relevant to the situation at hand, and we may try to study functions like this in the neighborhood of x equals 1, because these are actually, after all, the Lie numbers are of the shape A of rho or B of rho, and by putting a variable in and trying to study, making it a continuous function of some sort, trying to study it in the neighborhood of that point, probably will lead to more structure. So this is the background thought in our research. Now, the Riemann zeta function, of course, is the prototype of a vast galaxy of zeta functions. And much of this work that we have done is can be extended to what is called the Selberg class. Selberg was motivated in defining his class of zeta functions partly in an attempt to understand the Riemann hypothesis and see that there's some sort of building blocks for all zeta functions. The so-called primitive functions of the Selberg class are the building blocks of all the zeta functions, and therefore we expect that the Riemann hypothesis needs only be studied for those things. And so we do in our paper, I'm not going to do it in this talk, but we do in our paper enlarge our study to look at elements of the Selberg class and elements and special values of functions of this type as rho runs over non-trivial zeros of an arbitrary element of the Selberg class. So,
hypothesis do you put in order to get convergence, and in which region is your function well defined?
Yeah, that's a good question. Essentially, degree of A has to be strictly less than degree of B. And of course, if the degree of A is less than degree of B plus 1, then we have absolute convergence. And if it's just less than that, then we have conditional convergence, as long as.
And in the particular case where we are, yes, I will just disagree.
Yeah. Yes, it's okay because you've got rho at the end at the bottom. Yeah. And the degree is 1 less than but conditional convergence is just correct. Now, before I continue, let me kind of state the main results and then try to indicate how we prove some of our results. Let's see where this thing is. Okay. So here are theorems, before I run out of time. Theorem 1. So don't confuse that f of x with this f of x. Let f of x be equal to summation x to the rho over rho. Those of you who are familiar with the theory of beta function know that this occurs in the explicit formula for the prime number theorem. Let's look at this. Then look at the set x of all values of this function. The theorem is set x as at most one algebraic. And if you assume what's called Shanuel's conjecture, there is no such element.
Again, rho runs over a non-trivial zero.
Yeah, yeah. This is now for the rest of this talk. Yeah, yeah. So rho runs over non-trivial zeros. Assuming Shanuel conjecture, there is all are transcendental. All values. Here, let me just quickly tell you what Shanuel's conjecture is. If x1, x2, up to xn are q-linearly independent, then the transcendence degree of the field obtained by joining x1 to xn, easily x1, easily xn, is 3. So this is Shanuel's conjecture. So assuming that, then there is no such. We have that. And theorem 2 function f has infinitely many zeros. In one infinity, of which at most one is algebraic. And again, probably that thing doesn't exist. Yes, okay. And so this looks at the function in the region 1 to infinity. So x has got to be bigger than 1. And so one could inquire what happens if x is less than 1. And this is actually a fascinating consideration, fascinating question to investigate. What happens when x is actually less than 1? People embedded in classical analytic number theory often ignore this aspect of the question, because in trying to count prime numbers, you're trying to count primes up to x, and there are no primes of x for x less than 1. Therefore, you just don't bother with studying this thing. But it turns out this has interest in its own right. So let's, if you look at the function, so theorem 3. The set y given by the collection of values of f of x with x f of x minus x x in 0, 1 and algebraic valued. This has at most element, and in particular it has at most one algebraic zero in particular. This has everything. And here's the curiosity. If f of x is actually algebraic, and this is why the study of this function for 0 less than x less than 1 is interesting. If f of x is algebraic for some x in 0, 1, x algebraic, then Euler's constant is transcendental. So this is kind of a curiosity. So probably there is no such thing. Otherwise, this is one of the theorem. Probably there is no such
F1 is lambda 1. F1 is lambda 1.
F1 is lambda 1? Yeah, F1 is lambda 1 in the class. Yes, that's right. Yes. And then here are a few more things before I run out of time. Theorem 5. So here we've been considering special values at algebraic arguments. So it naturally begs the question, what happens when you look at non-algebraic arguments? Is there something that can be said in this context? And so in that context, we actually study the function f of root d pi root, so for any integer d, bigger than or equal to 1, suppose that f of pi root d x has a rational zero in the interval 0, 1 over pi root d. Suppose this happens. Then for the quadratic character, so let's say now this integer d, so we do need to assume, I think, square free d. Maybe we should assume that, yeah, d is not a perfect square. Otherwise, I think there's a problem here. D not a perfect square. We look at this, and then if chi sub minus d is the quadratic character associated to the field k equals q root minus d, the imaginary quadratic field, then maybe I should have too many thens here. If this happens, then L prime 1 chi minus d is not 0. Now, this is interesting from another perspective. About 15 years ago, Kumar and I had investigated the vanishings of derivatives of L functions in the context of the Selberg formula. And there we showed that if there exists a d for which L prime 1 chi minus d is actually 0, then e to the gamma is found. So it proves this nice, very beautiful result. And suspected that probably the hypothesis is never satisfied. So most of you know that classical analytic number theory, the proof of the Dirichlet's theorem on arithmetic primes and arithmetic progressions, involves the non-vanishing of L1 chi. But here now we're interested in the non-vanishing of the derivative. And this I don't think has been researched well in the literature. Partly because maybe there are not that many arithmetic consequences, but I can think of a couple. In this case, for example, in the context of the paper written with Kumar with class group L functions, and now in this context, this thing keeps on showing up, somehow linking the vanishing or the non-vanishing with transcendental number theory. So that's, these are the kind of the flavor of theorems that we have. So maybe before I stop, I just say a few words about what kind of methods we use. And as I told you, the general context of this paper is to study it in the setting of the Selberg class. So what are the methods we use? Well, we use a couple of methods in proving this theorem. The most important method is Baker's theorem. Tools in our proofs. So Baker's theorem. Baker's theorem is the following. If alpha 1 to alpha m are algebraic numbers, such that log alpha 1 and log alpha m are Q linearly independent, then one log alpha 1 to log alpha n, where one log alpha 1. Q bar linear. So you control this. So they should be non-zero, I guess. All logarithms don't make any sense. Non-zero algebraic numbers with this property. This is one theorem that's needed. The other theorem, especially in the context of Theorem 5, has to do with some of the material that we were teaching in the course here. And that has to do with Nestorenko's theorem. So Nestorenko's theorem. Let P of Z be the Weierstrass P function with algebraic invariance G2 and G3. In other words, i.e., as most of you know, the Weierstrass P function satisfies a nonlinear differential equation. Let that be given with complex multiplication by an order in the imaginary quadratic field. And let omega be a non-zero period. And eta, the corresponding quasi-period. Now, we didn't talk about quasi-periods in the course, but there's something called the Weierstrass Zeta function. The Weierstrass Zeta function, when you differentiate it, you get the Weierstrass P function. So think of the Weierstrass Zeta function as the integral of the Weierstrass P function. This new function is not an elliptic function. It's not a periodic shift, but it's almost periodic. There's some small shift, and that small shift is quasi. Okay, so I'll leave that for you to think about. Then once we have this setting, for any tau in the K, each of these sets are algebraically independent over. In other words, pi omega and either 2 pi I tau are algebraically independent. Pi eta either 2 pi I tau are algebraically independent. So this is Nestorenko's theorem, and it's applied in our context because we need to know, especially in the proof of this theorem here, we need something about pi, either pi root d, and the period. So you can see now how this part of the theorem is used. So there is a formula, the Selberg formula, for those who are familiar with it, will involve the period of the elliptic curve and these numbers. And when we specialize these values that come up, you end up getting a relation between these three. And therefore, if there was a zero, you'd get a dependence. So that's basically how the last part of the thing is used. But let me, before I stop, I think I'm almost running out of time. The focus of attention here is the idea is, if you think in terms of the prime number theorem counting, so this one Mongol function lambda n, log p, if n is the prime power, and 0 otherwise. And most of you know there's so-called explicit formula. I forgot the explicit formula, but maybe there's a constant in there somewhere. Yeah, there's a log 2 pi here somewhere. Okay, I may not get the sign right here. So this is valid for x greater than 1, it's explicit formula. And the fact of the matter is that although we're only talking about a special case of the problem that I'm outlining here, we can see that this sum here is almost a linear form of logarithms of algebraic numbers, except for this little log 2 pi, because the left-hand side is a linear form in logarithm. So that essentially was the starting point of our research. One needs to derive a variation of this, where instead of considering x to the rho over rho, you consider x to the rho over rho minus alpha. Because the idea is, as I discussed summation an over bn in the course, where the key idea was to develop the rational function into by partial fractions. You decompose this thing and move toward the study of sums of this sort. And then now, the explicit formula of classical prime number theory is the case when alpha is 0. So you have to rederive the explicit formula with this modification. And it can be done. Actually, I believe the first person who did it was Selberg in his early papers. But all these calculations and considerations were done for x bigger than 1. And the first person, and probably the only one, that ever considered the problem in the case when x is less than 1 seems to be Ingham. And Ingham came up with a very interesting formula. Let me write that down too. I think I'm running out of time, sorry. The Ingham formula is interesting in its own right, and that's where the Euler constant showed up. So it's the log 2 pi that I had somewhere here. There it is. You end up getting, if you do for n, so for x 0 less than x less than 1, there's also another explicit formula. And the explicit formula is minus log x minus gamma plus summation x to the rho over rho plus 1/2 log